What we're going to do is go over the properties of graphs. So properties of graphs are basically how we describe what a function looks like after we graph it. And right here on your screen you see basically all the key terms that you are going to need to know. You're expected to be able to talk about the graphs of all the functions that we'll do this year using this terminology. So let me really quick go over each of these. Domain, possible x values. This is whatever x is allowed to be. So when we look at our graph, we're looking horizontally to see where the graph would plot over the x values. We do need to watch out for the arrows at the ends of graphs, so that means that the pattern continues. So even if you don't see a graph on the left or right or extreme ends of your calculator, if there's arrows at the ends, you know that the pattern continues and you need to think, all right, the x's will keep on going. Of course, your calculator won't draw arrows. You just kind of need to infer that the pattern would. When you're graphing, you should put arrows at the ends of your graphs unless somehow indicated otherwise. The range is possible y values, and as you look at your graph, you're looking up and down. What can the y values be? And again, being careful of arrows. All right, you've done these before, but talking about increasing and decreasing, this can get tricky because for whatever reason, when you're doing math, you forget that you read left to right. And that's what you do when you're talking about it or asking the question, is the graph increasing or decreasing? You always look at it left to right. So for example, I'll draw over here. Let's say I have an axis like so. And let's say I draw, this is my graph. As I read left to right, notice the graph is going up. So we say it is increasing. Decreasing would be the opposite of that. So a decreasing graph could look something like this. We have it, we're reading left to right. It could look like this. It's decreasing, it's going down, but it's going down as I read left to right, not the other way. So we always want to read this way. Okay, so basically when we're asking increasing, decreasing, we're scanning the graph, looking at the y values as we scan left to right with our eyes. Roots are x-intercepts, so just really quick, here's a function. All these points are roots or x-intercepts. For the most part, be it for better or worse, in class we'll often use roots, x-intercepts, and zeros interchangeably, though they're not technically the same thing. You could have roots of an equation that actually don't show up on your graph, and so they wouldn't actually be x-intercepts because they're not showing up. And we'll see that as we go along in our current chapter. Special to note, roots are going to happen when y equals 0. So you set y to 0. Don't just assume that a root is a certain thing. Just actually do that and figure it out algebraically. Likewise with the y-intercept. So as we look at our function, I have my little picture right here. This is a y-intercept. So a y-intercept is when we cross the y-axis. This is when x equals 0. Substitute in. Don't be lazy. Figure it out. Okay, relative max, relative min. You're basically, for both of these, you're looking for the humps of the graph. So if we have our little plot right here, that is a relative max. And right here, that's a relative minimum. So a relative max is going to look something like this, and a relative min will look something like this. Now, do not get confused. When we're talking about an absolute max or min, we mean it's probably relative, but also it's the absolute highest on the graph. So in this picture of my graph, these are only relative max and mins because this graph goes lower and this graph goes higher than these 2 points. So these are only relative. But if I had a graph, say, like this, I have a relative max here, a relative min here, and a relative max here. But this one is an absolute max because it's the absolute highest that the graph goes. Likewise, if we have something like this, we have 3, I'll call them extrema. This is a relative min, relative max, relative min, but this one is absolute because it is the smallest that the graph gets. So you do need to pay attention to these tail ends, and just note those we'll be calling tail ends. We'll call that end behavior. We'll often be asked, what's the end behavior graph? What is it doing? What's the graph doing as you go very far to the left? And what is the graph going as we go very far to the right? And that'll give us our end behavior. All right, let's try a couple. Now, for those in my class, at the bottom in yellow, you'll see some complex expressions. What I want to see you turn in is on a whole separate sheet than your notes is those simplified as far as you can possibly simplify them. I'm not going to point them out again. Just know that I'm looking that you're actually listening to this video, so do the things in yellow at the bottom. All right, let's go through and answer these questions. So domain, possible x's. So what I'm going to look at is I see here that this is going up and this is going down, and this pattern would continue. I see it's kind of slanted, so it just kind of would keep going, right? And this would keep going. So the domain is going to be all the real numbers. Range, possible y's. I see this goes infinitely up and infinitely down. So that's also all the real numbers. Now, if we were going to do interval notation, we could say something like this, negative infinity to infinity with both of these. Now, this is not a point. This is interval notation. Right here, I use a parentheses to mean don't include. We can't ever actually get to infinity, so we never include those. And same thing for the range. We could write it like this. Okay, so intervals where the graph is going up, increasing. So as I scan left to right, I see that the graph is going up on this interval. So let's see, 1, 2, 3, 4, 5, 6. So that's negative 6, starting at negative 6, and going all the way to negative 2, not including because at these points, at our extrema, the graph is actually flat. It's not increasing or decreasing. Now, we don't have to use interval notation. We could use inequality. So I could say negative 6 is less than x is less than negative 2. And notice you always put the smaller number first when you're using inequalities. So we don't want this backwards. We wouldn't want the negative 2 on the left-hand side here and the negative 6 right here. We just always write, in convention, the smaller number first. So that's sandwiched. All right. Is that the only place it's increasing? Well, in this graph, yeah, that's the only place it's increasing. So as I look at this graph, I notice from negative infinity to negative 6, notice the graph is going down. And from negative 2 to infinity, I notice also the graph is going down. So I have two areas where that happens. So in interval notation, I could say negative infinity to negative 6. And also, I'll say or. I think you could say an and right here. Negative 2 to infinity. Now in inequality notation, we would write negative infinity. Let's see here. Actually, we would want to do negative 6 is x is less than negative 6. And this would be x is greater than negative 2. So I think the interval notation might be a little bit better for listing these than the inequalities. All right, roots. I have negative, let's see, 2, 4, 6, looks like 7. So negative 7, negative 5, and 4. Right here is a root. Y-intercept, I don't know what it is exactly, but 1, 2, 3, 4, 5, 6, maybe 6.5. Relative max, that would be right here, is a relative max. So I have a relative max at the point negative 2. Let's see, 2, 4, 6, 8. Relative min, looks like I have negative 6, negative 3. This is a relative min. And there are no absolutes because of the arrows on the ends of the graph. Alright, so this is basically the same graph, just flipped around, it appears. So our domain, again, is going to be the real numbers, and our range is the real numbers, and I'm looking specifically at these arrows. I'm going to go ahead and knock the roots out, so I have 1 and 3. And 2, 4, 6, 8, looks like negative 8. Y-intercept, right here, so we have 1, 2, 3, 4.5. Alright, absolute max, I have right here, negative 2, 8, 2, 4, yep. And relative min, I have right here. No absolutes because of the tail ends. Alright, now intervals of increasing, decreasing. So as I'm scanning the graph left to right, and I'm asking, what is the y value doing as I go left to right? Well, it's increasing until I get to negative 2. Negative 2. Now in inequalities, that would be from negative infinity to negative 2. So it's increasing from x is less than negative 2. Decreasing from negative 2 to 2. I see it's going down as I scan left to right. Always scanning left to right. So since it's going down, negative 2 to 2. And then it's increasing again, starting at 2 to infinity. So it's increasing from 2 to infinity, which would be x is greater than 2. Alright, we hit all of those. Alright, this graph is a little bit different. So let's see. Domain, I see these tail ends. Now, even though this is going sharply up, in order for it to continue going up, the x values would have to continue to decrease. So arrows at the ends, we're basically going to get real numbers here. Now, the range is a little bit tricky. Because we don't have the real numbers, we have a lower value here. So we don't go below negative 3. So we could say y is greater than or equal to negative 3 as our range. And the way to write that using intervals would be negative 3 to infinity. This time we'll include the negative 3, so we'll make sure we use a bracket right here. Roots. I'll do the increasing, decreasing last. So roots, I have negative 3 and looks like negative 7. Y-intercept looks like I have 3. So remember, y-intercept is where x is 0, and the roots are where y is 0. Relative max, none. I don't have any. I have this weird little thing going on right here, but it actually doesn't. It actually doesn't have a hump right there. All right, minimum, right here. So what is that? Negative 5, negative 3. And this is the absolute lowest that it gets. So negative 5, negative 3 is an absolute minimum. Alright, let's take a look at increasing, decreasing. So we're decreasing from negative infinity to negative 5. And then we're increasing from negative 5 to infinity. So we could write this as x is greater than negative 5, x is less than negative 5. And again, at this point, it's neither increasing or decreasing. Alright, we got a gap right here. So that's going to be interesting to figure out. So our domain, possible x's. Now, because this is bubbled in, we actually do have a value at 2. But our range is going to be interesting. So our domain is the real numbers. Now for the range, I have a weird gap. So what am I going to do right here? Apparently, we don't have any values from negative 3 to negative 5. But I do have values from negative 5 to, and this pattern continues. Now, it levels out right here. And that's implying something that we call an asymptote. And we'll do more of those coming up. But the only way to know for sure that you have an asymptote would be, or that you would indicate that you have one, is if you draw a dotted line. And I'm actually going to go ahead and do that. I'm going to say that I have a dotted line here, and that this graph actually never crosses this dotted line. It gets close to it, but doesn't cross it. So what are we going to say? So we don't have a range that's going to negative infinity, but we do go to negative 5 to, let's see, negative 6, 7, 8, 9. But we never actually get to negative 9. So our range is negative 5 to negative 9. We never actually get to negative 9. But we do, because this is bubbled in, actually get to negative 5. So we'll include that. And then we have, I think we should use an and right here. I'm going to use an and. From negative 3. Now, this is not bubbled in, so we don't include it. So, negative 3. And then this does go up to infinity. So, infinity. Now, how would we write this using inequalities? Well, we'd say negative 9. Oh, I'm dumb. I did this backwards. My bad. Smallest number first. Smallest number first. Alright, that's fixed. So, negative 9 is less than y is less than equal to 5. And we have from negative 3 up, so we'll write y is greater than negative 3, but not including negative 3. Alright, increasing, decreasing. As I look, again, when we're doing increasing, decreasing, we read left to right. So, even though this arrow is pointing the other way, when I'm asking this question, I'm reading left to right. And as I read left to right, the graph is going up. In fact, it's always going up the whole time. So it's increasing all the time. So that's going to be from negative infinity to infinity. And it's decreasing, not at all. Roots. I got one right here. That's 6. And y-intercept, let's see, 2, 4, 6, 8. So negative 8. Now, this is a point. All right, just want to draw your attention. This is a point. Context matters. These are interval notations. So they are not points. So context is going to matter for how you're reading these things. Relative max, none. Relative min, none. Absolute max or min, none. We have none of these things. Alright, that concludes this. On Google Classroom, check for a Kahoot code to check your understanding of this. Use your first name followed by your last initial. That way I know who did what.